figure out the moment of inertia about the center of mass due to one chunk, the moment of inertia about the center of mass due to a second chunk, the total moment of inertia would be those two chunks added together. Okay. Second, there's something called the parallel axis theorem. I can't remember if I proved it or not to you back in strength of materials. I'm not going to reprove it right now. I'm just going to represent it so see if we can use it. If we decide to reprove it, we'll do that maybe later today, maybe Wednesday, maybe on the exam, something like that. This tells us that the moment of inertia about an incorrect spot is equal to the moment of inertia about the correct spot plus some extra amount. Okay? So in this case, what we mean by our I right is our center of mass, because we're using the sum of the moments equals the moment of inertia times theta double dot, and that equation was valid if we're calculating everything with respect to our center of mass. So we have this relationship. What will be larger, the moment of inertia about the center of mass or the moment of inertia about some other spot? Looking at that equation. Some other spot. Well, I guess it depends. Is this term going to be positive or negative? So what would need to happen for this term here to be negative? The mass would have to be negative. Okay, so I'd have to have negative mass. So, Bonnie, with us?
I'm sorry, it's we'll get it in 2 seconds. I'll leave it.
Okay. Yeah, you can do it on the column.
Yeah.
Wait, so that's m times d squared, or it's md squared?
It's m times d squared. So it's the mass times the distance squared.
Oh,
That was quick, Bonnie. So this is the mass of your object, and the d is the distance that you're moving it from the center of mass. So in order for this to be a negative number, you'd have to have a negative mass. So whether I move it up or move it down, whether I move it a positive distance or a negative distance, that distance squared will always be a positive number. So the moment of inertia when calculated about the center of mass will be smaller than if I calculated about a different point. Okay. So we're calling this I wrong. It's not the value that you ultimately want. It could be, though, that from your problem you have an easy time figuring out I wrong, but you're trying to find the correct value. Okay, so this tells you a way to get the correct value in terms of I wrong. So if you can get the I wrong quickly, maybe you can just take the I wrong and subtract the mass times the distance squared. And that distance would be the distance between the center of mass to wherever you calculated the incorrect moment of inertia about. So for example, we're going to use this, or I'll let you use it in a moment. I'm just going to outline the process. I'd like to find the moment of inertia of our baseball bat that we had last class. Last class we decided that the moment of inertia about the center for any rod was equal to 1/12 the mass times the length squared. So you did that in general and proved that little relationship. That gave you the moment of inertia about the center of a rod. So suppose I use that formula to get the moment of inertia for this bottom section of the baseball bat right here. If I use that formula to get the moment of inertia for this bottom section, that's actually giving me I wrong. It's giving me the moment of inertia about that point. I really want to find out the moment of inertia about that point. Okay? So this formula is giving me the moment of inertia about the center of this rod, spinning it this way. We actually want the moment of inertia here. So this formula tells me the moment of inertia about the center. I want to figure out the moment of inertia about that point, because this is the center of the baseball bat, not just the bottom handle. This is the center of the baseball bat. Okay, I can do the same thing for the top of the bat. In fact, I can use this formula to calculate the moment of inertia for the top half of the bat. The top half of the bat, the center of the top half of the bat would be halfway through it. Okay? So if this was 0.5 L for the bat, its center of mass would be a quarter of the way down. is L. That M stood for meters, not mass. This is the center of mass where it's located. So initially I had the unit on there. It was 0.65 times the length of the bat, whatever that worked out to. So how far should I have to shift to the center of mass, or the point where I'm calculating my moment of inertia, to go for this top chunk to the center of mass of the bat in total? How far would that need to be shifted?
Well, the difference between the two?
What is it? Okay.
Wait,
Yeah.
Vaughn's saying
What's
negative
shifting?
0.1.
Yeah, down.
Well,
Which
if I
dot?
use this formula to calculate the moment of inertia of the about the center for this top half of that baseball bat,
Okay.
that's going to give me the moment of inertia about this red dot right here.
Okay.
I actually want the moment of inertia about the blue dot. The blue dot is the center of mass of the bat. I need to get the moment of inertia of the bat. So I'm going to do it in two chunks, this chunk and that chunk. But to do it correctly, I need to shift each of these chunks. So I need to figure out how far I have to shift each chunk. So what's the difference between this point and that point? 0.1. I agree. And maybe you can figure out the difference between that point and that point. What's the difference between those 2 points?
0.4?
Roger's got it. Okay? Alright, so I want you to figure out the moment of inertia of the bat. We couldn't finish our discussion of center of percussion without getting this moment of inertia. So let me pull you all up to the whiteboard and work in your team of 2 to figure that one out.
Don't worry, leave it there. Have an
You'll have an L in it, but your answer should be like 0.23
L or is
L squared.
Okay.